Welcome to Homework Lib.
Okay, so this question is a little difficult than the others. And basically, what is happening here is that we have a hydrogen atom initially at an state. Let's put here a state of n, described by the quantum numbers n equals 3, l equals 1, and j equals 3 halves. We also have to consider the same hydrogen atom, but this time in a different state, which is n equals 3, l equals 1, and j equals 1 half. Okay, so the last quantum number is different here. And what is happening here is that we need to calculate the wavelength, actually the change between the wavelength of an emitted photon when the atom, the particle, sorry, makes a transition from this first state here to a second state, which is n equals 2, l equals 0, and j equals 1 half. And we have, when the electron makes the transition between these two states here, as we know, he emits a photon, and this photon has associated wavelength. And we need to consider both this transition, then this transition, find this is lambda 1, I don't know, and this is will be the wavelength of the second emitted photon, and then we have to calculate the change in this wavelength. So we need to calculate uh, delta lambda, which is lambda 1 minus lambda 2. Okay, so it's a question a little complicated to understand, and a little complicated also to think how we actually going to solve this, because the obvious way to solve this problem is to calculate the energy of the emitted photon and this first transition, for example. So we have energy transition there, delta E, and this gives us, I don't know, uh, delta E is going to be hc lambda 1, for example. And then we calculate lambda 2 with another energy transition, and then we can find the difference of the wavelength. But, but there is a smartest way to calculate this. Actually, let's see, it's a funny way to calculate this. How are we going to calculate this? We're going to use an equation that we already know. And why we are going to use this equation? Because the change in the energy between, let's call this 1, 2, and 3. Okay, this is both the states. The difference of energy and wavelength also between the first and the second state is really small, comparable with between 1 and 3 or 2 and 3. Therefore, we're going to discover right the answer, which is delta lambda that we want, minus lambda divided by the energy of the photon divided by the energy transition between 1 and 2. So we're going to calculate an energy transition between 1 and 2. Okay, we're going to find, and when we do this, we're going to find the wavelength difference between the two states, which is precisely what we want. So we're doing in a different way. But how we calculate the energy when we have to consider the J quantum number? Well, this is also a table in the textbook. Is an ugly equation, but let's see. The energy when we have to consider the quantum numbers n and j are described by negative 13.6 divided by n squared. This is familiar. But we have a modification, which is 1 plus alpha square divided by n square that multiplies n divided by j plus 1 half minus 3 quarters, and this is the way we calculate the energy considering the quantum number j. Alpha is known as the fine structure constant. Alpha has a value which we're going to put here of 7.297 times 10 to the minus 3. So this is the numerical value of the constant. And well, let's calculate first of all this quantity here, delta of energy. So the transition between 1 and 2. This will be calculated in that way. So change in the energy will be the difference between the energy of the state 3 halves minus the energy of the state 3 1 half. Okay, so substituting this in the equation, we have 13.6 divided by 9 that multiplies 1 plus alpha square divided by 9 that multiplies 3 halves plus 1 half minus 3 quarters minus 1 minus alpha under 9 that multiplies 3 1 half plus 1 half minus 3 quarters, and we can simplify this cutting the ones and here, putting the alpha divided by 9 on evidence. Therefore we have a negative here, negative 13.6 divided by 9 that multiplies alpha square divided by 9. All this multiplying, let's see, we have 3 halves but plus 1 half. This is 4 half, which gives us 2. So we have 3 halves minus 3 quarters minus 3 plus 3 quarters. Okay, therefore cut here, and calculating what is left using the fine structure constant, we get that the change delta E of the energy will be 1.341 times 10 to the minus 5 electron volts. So as we can see, is really small change in the energy. Okay, what is the second thing we need to calculate here? So the second thing we need to calculate is both the energy and the wavelength of a transition between 1 and 3. Okay, so let's do this calculation here. Is actually a transition when we go from n equals 3 to n equals 2. So this is the transition we are calculating right now. So using the already know delta E, so let's call this EP, which is the delta E, or if we want to simplify explicitly open this, is E3 minus E2. Therefore this is basically negative 13.6 that multiplies 1 divided by 9 minus 1 divided by 1/4. All this will be equal to, let's see, Calculating this, we got 1.889 electron volts. Already we can see the difference between the energies with the transitions. The transitions between the principal quantum number n is much greater in the energy than the difference between the spin. Okay, so now with this energy, we're going to calculate the wavelength associated. So the wavelength will be equal hc divided by ep, which is the energy of the photon. Therefore, this is 4.136 times 10 to the minus 15. That multiplies the speed of light, which is 3 times 10 to the 8 divided by 1.889. This gives us a wavelength of 656 nanometers. Okay, and now we can finally use our equation. So we can finally use this equation and calculate the change between the wavelength of the two emitted photons. So let's put in red the final answer. So delta lambda will be equal 656 nanometers divided by 1.889. That multiplies delta E, which is 1.341 times 10 to the minus 5. Therefore, this is equal negative 0. I forgot the negative sign, sorry. Negative 0.000466 nanometers. As we can see, the change in the wavelength is negative. Therefore, we can understand that J equals 1/2 has the longer wavelength. Has the longer wavelength than J equals 3/2. Okay? So this is the final answer. Thanks for watching.